Look at your lower back. Right there, at the bottom of your spine, there's a small triangular bone. Most people never think about it. Doctors call it the coccyx. But do you know what it actually is? It's a tail. Not a working tail, not a tail you can wag or swing, but it's the leftover, folded up remains of a tail your ancestors actually had millions of years ago. Every human being on this planet, you, me, your friends, your family, we all start life in our mother's womb with a tail. For a few weeks, every human embryo grows a small tail, just like a monkey embryo does. And then, one day, that tail disappears. The body reabsorbs it, and we're born without one. So here's the real question this video is going to answer. If we once had tails, where did they go? And why, out of every single animal that evolved a spine, did our ancestors specifically decide we don't need this anymore? This is not just a biology lesson. This is a detective story. And it took scientists almost 200 years and one moment of pure luck to finally solve it. Let's go back in time. Imagine a forest, not any forest, a dense, warm, humid forest, somewhere in Africa, about 25 million years ago. Long before humans, long before Homo sapiens, long before anything that even looks remotely human. In this forest lives a small, furry, monkey-like creature. It has 4 limbs, sharp senses, and, like almost every other mammal on Earth at the time, a long, functional tail. Now, why does this creature need a tail in the first place? Think of it like a tool, not a decoration. If it's climbing trees, the tail acts like a 5th limb, balancing its body, gripping branches. If it's running on the ground, the tail works like a rudder, the way a lizard's tail helps it turn quickly. If insects are bothering it, the tail becomes a fly swatter. For almost every mammal, dogs, cats, monkeys, mice, the tail is genuinely useful. It's not wasted body real estate. Evolution doesn't usually keep useless things around for millions of years. So, somewhere in this creature's lineage, something happened that made the tail less useful than the energy it cost to grow it. And that something would eventually lead to apes, gorillas, chimpanzees, orangutans, gibbons, and to us. Every single one of these species, called hominoids, has no external tail. Every monkey species still has one. That line, hominoids versus monkeys, is exactly where the tail disappeared. For 200 years, since Darwin himself wrote about this in The Descent of Man in 1871, scientists knew tail loss happened. What they didn't know was how. What actually changed inside the DNA to switch the tail off? This part of the story has a very human moment in it, and I want you to really picture it. In 2019, a molecular biologist named Bo Shah was a graduate student in New York. Like a lot of people that year, during an accident, he injured his tailbone. He was in pain, sitting carefully, unable to sit normally for weeks. And in that pain, a strange thought crossed his mind. Why do I even have a tailbone if I don't have a tail? What happened to it? Most of us would take a painkiller and move on, but Bo Shah was a geneticist. So he did what geneticists do. He went looking for the gene. He knew scientists had already found around 100 genes in mice that, when mutated, can affect tail length or tail shape. So his logic was simple. Somewhere among genes like these, one of them must have changed in the ancestor of apes, and that change removed the tail completely. This is exactly like being a detective with 100 suspects and only one crime. He had to go through the evidence, gene by gene. Eventually, his attention landed on a gene called TBXT, sometimes just called T or brachyury. This gene is incredibly important. It's one of the genes responsible for building the spine and the tail while a baby or a baby animal is still developing as an embryo. Almost every animal with a backbone has a version of this gene. So, Bo Shah compared this gene across many species, humans, chimps, monkeys, mice, looking for differences that exist only in tailless apes and humans and not in tailed monkeys. And he found something odd. Sitting inside the TBXT gene, in a region that doesn't even code for protein, was a small chunk of repetitive DNA called an ALU element. Now, let me explain ALU elements simply, because this is the heart of the whole story. Think of your DNA as a very long book made of billions of letters, split into chapters, genes. An ALU element is like a rogue, self-copying paragraph that exists only in primates. It's sometimes nicknamed a jumping gene because over millions of years, copies of it literally cut themselves out and paste themselves into random new locations in the genome, like a chaotic autocorrect that randomly inserts the same sentence into different pages of the book. Most of the time, when an ALU element jumps into a new spot, it does nothing important. It's junk, harmless. That's actually what scientists expected, here too. But Beauchamp noticed something remarkable. There wasn't just one ALU element near this part of TBXT. There were two. One ancient one that monkeys also have, and one brand new one that only apes and humans have. And critically, they were facing in opposite directions to each other, like two magnets pointed at one another. Here's where the real aha moment happens, and I'll explain it with a simple example. Imagine your gene is a recipe, written as a long sentence, and your cell has to read the whole sentence to build the tail properly. Normally, that reading happens smoothly, start to finish. Now, when two ALU elements land close together, but pointing in opposite directions, something strange happens during reading. The cell's machinery gets confused. It's like two people who wrote the same sentence backward, right next to each other in the recipe book. When the cell tries to read through, it accidentally treats these two facing ALU elements as a signal to skip a piece of the recipe entirely. Specifically, a segment called exon 6. This is called exon skipping. The result is that the ape version of the TBXT gene doesn't just get slightly changed. It gets a chunk of it left out, like a paragraph that got torn out of the instructions. And this incomplete version of the gene doesn't build a proper tail. Depending on how much of the normal gene versus the skipped version is present, the tail comes out shorter or doesn't grow at all. To actually prove this, Beauchamp's team didn't just guess, they tested it. They used gene editing tools to insert this exact same pair of ALU elements into mouse embryos. And the result was extraordinary. The mice were born with little to no tail, exactly as predicted. That's the moment. Roughly 25 million years ago, we believe this accidental genetic typo appeared in the ancestor of all apes, including us, and simply never went away. Because it clearly wasn't hurting survival. If anything, it may have helped. This research was finally published in the journal Nature in 2024, closing a 150-year-old mystery that started with Charles Darwin. Now, here's the part that really connects this ancient accident to who we are today. Scientists believe losing the tail wasn't just a random cosmetic change. It may have been one of the pushes that eventually allowed our ancestors to walk upright on two legs, something called bipedalism. Think about it simply. A tail is useful for balance, on all fours or in trees. But once ancestors of apes began spending more time upright or moving differently through trees using their arms, like gorillas and orangutans do, a long, trailing tail becomes less useful and might even get in the way.
So, losing the tail may have been one small piece in a much bigger puzzle that eventually led to humans standing up, freeing our hands, and over millions of years, building tools, art, and everything else that followed. That means this single, accidental mutation, this one clumsy jump of a piece of DNA 25 million years ago, may be quietly connected to the fact that you're able to type on a phone, write on a whiteboard, or hold a cup of chai right now. But here's something beautifully honest that this research also revealed. Evolution rarely gives something for free. When the researchers created these tailless mice, some of them were also born with a condition called a neural tube defect, a problem where the spinal cord doesn't close properly during development. In humans, this same category of condition affects roughly 1 in every 1,000 babies born. Conditions like spina bifida. Scientists think this might be the cost of that ancient mutation. The same genetic accident that removed our tail may have also slightly increased our risk, generation after generation, of this type of birth complication. It's a powerful reminder. Evolution isn't a perfect designer. It's not choosing the best option from a menu. It's just millions of accidents tested by survival, generation after generation. And the ones that don't kill you get kept, flaws and all. So, the next time you sit down and feel that small bone at the base of your spine, remember, it isn't just a random bone. It's a message from 25 million years ago. It's proof that inside every one of us is the folded up memory of an ancestor who once climbed trees, balanced on branches, and used a tail to survive. And the whole story of how we found this out, it started with one curious person in pain from an injury who, instead of just complaining, asked why. That single question turned into years of research, gene editing experiments on mice, and finally, an answer to something Charles Darwin wondered about more than 150 years ago. That's the beauty of science. Sometimes, the biggest discoveries about who we are don't start in a fancy lab. They start with a simple, honest question that a curious mind refuses to let go of. If you found this interesting, let me know in the comments, and I'll see you in the next video.